Hey everyone and welcome. Today we're tackling a really interesting graph problem from Leetcode called power grid maintenance. We'll break down the logic step by step and explore a couple of very clever ways to solve it. Alright, let's start by understanding the setup. We're given a visual representation of the problem, but let's talk through what it all means. So at a high level, we're in charge of a city's power grid. It's made up of a bunch of power stations, all linked together by cables. Our main job is to process a list of events, which the problem calls queries, that happen over time. These events come in two main flavors. First, there's a maintenance check. If the station being checked is up and running, it just handles the check itself, no problem. But if it's offline, we need to find a backup. The rule is to find the online station with the absolute smallest ID number that's still part of the same connected grid. And if every single station in that part of the grid is down, well, then we report back with a -1. The second type of event is much simpler. A station just goes offline. So to summarize what we're given, the total count of stations, a list of all the direct connections between them, and of course, the list of queries we need to process. Our final goal is to produce a single array that contains the answers to all those maintenance checks, in the exact order they were asked. Let's walk through an example to make this really solid. We have 5 stations, all connected in a single line. At the start, all 5 are online. The first query is a maintenance check on Station 3. Station 3 is online, so it handles the check itself, and our first result is 3. Easy enough. Next up, Station 1 goes offline. The grid is still one connected piece, but our active stations are now 2, 3, 4, and 5. Now another check comes in, this time for Station 1. Since it's offline, we have to find the online station with the smallest ID in its grid. Looking at our active set, the smallest is 2. So the result for this query is 2. Then, Station 2 also goes offline. Our list of active stations is shrinking. It's now just 3, 4, and 5. The final query is a check on Station 2. It's offline, so we again look for the smallest active station in its grid. Right now that's Station 3, so our last result is 3. This gives us our final output array. 3, 2, 3. Just a quick heads up. We'll be walking through the solutions using Python, but don't worry if that's not your main language. The logic is what matters, and I'll be showing the full code for Java, C++, and JavaScript towards the end of the video. Okay, let's dive into our first approach. The trickiest part of this problem is that when a station goes offline, our smallest online station for a whole grid might change. Keeping track of that as things disappear is complicated. So here's a really clever idea. What if we process the queries backwards? By starting from the end, a station going offline now becomes a station coming back online. Adding things back into a structure is often way easier than taking them out, and this is a perfect use case for a data structure called union find. Okay, we've talked about the big picture and the reverse logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first, and don't worry, after that, we'll walk through the most important sections together. Alright, here's the full Python code for the union find approach. It might look a bit dense at first, but we're about to break it down piece by piece. First, we set up our tools. We create a parent array for the union find structure, where each station initially is its own parent. We also have a min online station array. This is key. For each group, it will track the smallest ID of an online station in that group. Inside the main function, we first do a quick pass through all the queries, just to find out which stations will ever be taken offline. We store them in a set for quick lookups. Now remember, we're working backwards from a final state, so we figure out which stations were never taken offline. We then build our initial union find structure by connecting only these always-on stations. This gives us a baseline of the power grid with all the offline events having already happened. This is the core of the reverse logic. We loop through the queries from last to first. If we see a maintenance check, we just find the group that station belongs to and look up the stored minimum online station for that group. Easy. If we see a go offline query, we do the opposite. We add that station back to our set of online stations. Then, we look through the original connections list and union this newly online station with any of its neighbors that are also currently online. At the very end, we just have to reverse our results array to get the correct order. Okay, let's look at a completely different way to solve this time processing the queries in the correct, forward order. The main idea here is to first figure out all the separate connected grids. We can do this with a standard depth-first search or breadth-first search. Then, for each of these grids, we'll use a min priority queue. which is a special data structure that's super fast at always telling you the smallest item it contains. This sounds perfect, right? The only catch is that efficiently removing a random station from the middle of the queue is tricky, so we'll use a technique called lazy deletion. This forward processing approach with priority queues has a different structure. Let's get the full code on the screen, and then, just like before, we'll dissect the important parts. And here is the Python code for the second approach, using a graph traversal and priority queues. You can see it has a distinct setup phase and then a processing phase. The first step is all about understanding the grid structure. We build a standard adjacency list to represent the graph. Then, we loop through every station. If we find one we haven't visited yet, we start a traversal, like a BFS, to find every single station connected to it. This group of stations is one component, or one grid. We gather all the stations in that component into a list, and immediately turn that list into a min heap, which makes finding the smallest one super fast. We repeat this until all stations belong to a component. Next, we create a simple map so that for any station, we can instantly know which power grid or which priority queue it belongs to. We also create a set to keep track of all the offline stations. Then we loop through the queries in order. The easy one is type 2. If a station goes offline, we just add its ID to our offline set. We don't touch the priority queue yet. That's the lazy part. Now for the maintenance check and the lazy deletion. When a check comes in for a station, we find its corresponding priority queue. Then comes the magic. We look at the smallest item at the top of the heap. Is this station in our offline set? If it is, it means we should have removed it already. So we pop it off and look at the new smallest item. We keep doing this until the station at the top is one that is not in our offline set, or until the heap is empty. Whatever is left at the top is our answer. So how do these two methods compare in performance? The union find approach is extremely fast. Its time complexity is nearly linear, where m is the number of connections and q is the number of queries. That alpha symbol represents a function that grows so slowly it's considered constant for all practical purposes. The space is linear to the number of stations. The DFS approach is also very good. Building the graph takes time proportional to the number of stations and connections. Then for each query, the heap operations could take up to log c time. Its space complexity is a bit higher, as we need to store the entire graph. Alright, that covers the main logic in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. You can pause the video here to take a closer look at the implementation. I've used the union find approach here. Next up, here is the C++ version of the solution. Again, feel free to pause and review the code. It follows the same reverse query union find logic. And finally, here is the solution in JavaScript. Hopefully seeing it in a few different languages helps solidify the concepts behind the reverse processing union find method. So let's wrap it up. The biggest takeaway here is that whenever you see a problem involving deletions or elements going offline, you should always ask yourself, can I solve this backwards? This simple trick can turn a hard problem into a much easier one. The union find data structure is your best friend for tracking connected groups. And, as an alternative, using priority queues with a lazy deletion strategy is another powerful technique to keep in your toolkit. Alright, before we finish up, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill, so I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads, and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now, down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra, but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.